In the quantum chemistry course, so far we have applied the time-independent Schrodinger's equation to different systems. This has finally culminated to the fact that we are able to understand how the hydrogen atom solutions look. So let me quickly reiterate some of these aspects so that we get calibrated on this stuff. So we are having a vector here which joins the center of mass where the electron ends up moving about the center of mass with respect to the nucleus. Of course, the nucleus is going to be quite close to that of the origin here because it's much more heavier than that of the electron, about 3 orders of magnitude higher than that of the electron. And then the usual angles were defined, right? Theta and phi were defined, where r is the distance of the electron from that of the origin, that is from the center of mass. If you assume that the nucleus is much heavier, you can assume nucleus itself is at the origin. Okay, so now that we end up having this, we ended up solving the Schrodinger's equation for this case, where you said h psi equal to E psi, where the Hamiltonian was written as minus h cross square by 2 mu, where mu is the reduced mass between that of the nucleus and the electron, del square minus E square by 4 pi epsilon naught times r, right? So where this comes up from the kinetic energy contribution, while this ends up coming from the potential energy contribution. So this is what was set up. Then we ended up converting the del square into r theta phi, and therefore this got reduced to minus h cross square by 2 mu 1 over r square dou by dou r square dou by dou r, then plus 1 over r square sin theta dou by dou theta sin theta dou by dou theta plus 1 over r square sin square theta dou square by dou phi square. So this is how our Laplacian looked after transforming to r theta phi. Of course, this is already in r, so therefore we were able to combine these. And of course, after deduction, we were able to reduce a significant part of it. Once you take r square out, we were able to appreciate the fact that this has the formulation of something of the sort of L square. Of course, L square by r square. The r square will come out and will become 2i. And therefore, we resorted to writing the solution of NLM as r times YLM, where y were the solutions of the spherical harmonics, right? And then we were able to write what is this RNL. N minus L minus 1, the factorial, divided by 2n, n plus L factorial the whole cube, the whole power 1 by 2, r power L, e power minus r by n a naught, 2 by n a naught, L plus 3 by 2, right? And then we had L, n minus L minus 1, and then the superscript 2L plus 1, where we said these are the Laguerre polynomials, right? There was a small mistake that was done. Of course, with the superscript here, they become associated Laguerre polynomials. There was a subtle mistake that happened in the previous class where this associated ones were not written correctly. So I'm going to rewrite some of the Laguerre polynomials. So L0 is equal to 1. L1 is given as, I'm looking at a set of tables and writing it. None of this is from memory. L2 is x square plus 4x plus 2. And the associated Laguerre polynomials, so some of them, so let me write them. L00 remains 1, similar to this, and L01 will be minus x plus 1. L20, once again a small mistake, this should be L10. L20 is going to be x square plus 4x plus 2. L01 is going to be 1. L11 is going to be minus 2x plus 4. We don't have to worry about any of this, as we will be looking into this class how one can identify a given orbital just by looking at the functional form. Okay, L0, 2 is 2 and so on. You can take a further look at the DJ Griffiths textbook, right? And Griffiths textbook chapter section 4.2 will give you the further associated Laguerre polynomials. Okay, after having understood this, we also realized that every wave function will be associated with an energy, and in this case the energy comes up as minus E square by 8 pi epsilon naught A naught over n square, right? Where the A naught is the Bohr radius, and this gets reduced to minus 13.6 divided by n square EV. And this has been seen by us already in the Bohr model. So we are able to see a correspondence of energy that has been deduced using the quantum theory and using the ad hoc assumption that Bohr had introduced, saying that the angular momentum is quantized, right? So now, having understood this, let's go further with what we want to do. We were able to further realize that the expectation value of R goes as n square, indicating that as you go farther away in the principal quantum number value, the electron resides much farther from the nucleus. And one other important aspect we were able to realize was that the most probable place where you would find the electron was given at A naught for the 1s orbital, but the expectation value was something like 3 by 2 A naught. So this gives you an idea. So let's try to plot it, the probability as a function of R over A naught. We were able to see a function that looked like this, where the most probable is at A naught. On the other hand, the average comes up at 3 by 2 A naught. So this is an important thing to realize, where we are moving away from the definition of orbits, where orbits were a defined set of radii from the nucleus where the electron could be found. And we are moving away from a discussion where we are able to see there is enough probability that is present before and after this given A naught. Okay, so this is the difference that ends up coming for the discussion of the orbitals. So these are the solutions that end up coming for the hydrogen atom. Okay, and as we are able to see the wave functions of the hydrogen atom, we are able to appreciate a few facts here, meaning that the psi n, l and m, n is the principal quantum number, l is the angular momentum quantum number, and m is the magnetic quantum number. L is also called the azimuthal quantum number, and in many places people tend to write the magnetic quantum number as ml, indicating that the L value restricts the values of m, where L goes from 0, 1, 2 until n minus 1, and m goes between 0 plus minus 1 plus minus 2 in integer steps until plus minus L. And these are all the values that you end up seeing in this case. Okay, and the moment you start to have m value that's greater than or different from 0, you get a plus minus 1 value that also ends up coming up here. And the important aspect one has to understand is that we see a polynomial part and also the e power minus r by n A naught part. The sigma is, sorry, I've written rho here. The sigma is defined as r by A naught, where A naught is the Bohr radius, and therefore you are able to realize the n quantum number can be easily read out of the e power minus sigma by n term that comes in each of this. So if you pay close attention, you are able to realize that the e power term without the imaginary part, there are two e power terms, one with the imaginary part, one with just the real part. The real part, one is able to give you the n quantum number. And moving forward towards the L quantum number, we have to look at YLM parameter or the R power L parameter that we saw in the previous slide, right? The R power L comes from something of, you would realize that for the s orbital it's going to be r power 0 since the L value is 0. Of course, there are other terms that would end up coming, that is due to the Laguerre contribution that is going to be present. Let's take an easier case to understand this. When you're taking a look at the p orbital, you see a cos theta and sin theta term. This is nothing but the y10 term that ends up coming. This is cos theta and then the y1 plus minus 1 term was a sine theta term. So you realize that if you have a cos theta or a sine theta, basically you had PL of m as x for L equal to 1. That's the same thing that we end up seeing here. So you have cos theta or sine theta, you end up predicting what is the L value. Yeah. So having seen this, you are able to also appreciate the fact, okay, so this indicates that L value is 1. This indicates the L value is 1. The moment you go to squares of it, cos square theta is nothing but x square in the term, and sin theta cos theta is going to be square root of 1 minus x square, which has a x power 1 type dependence, and cos theta which has an x dependence. So you're able to realize that this goes into x square. So when L equal to 2, you're going to have theta times theta, basically x square type of term starts to come up. So this helps you predict what is the L value. And going to the m value, you might remember the m value can be predicted with the e power im phi. So whenever the m value is 0, you're going to have no imaginary contribution, as in this case, as in this case, and as in this case. Right? Of course, the s orbitals by default will not have any imaginary contribution because you're looking at y00, which is equal to 1. Right? And now you're also able to appreciate the fact that the same s orbital, as you go from 1s to 2s to 3s, starts to have a Laguerre contribution that ends up coming. So what is the Laguerre contribution that we are talking about? This is the Laguerre contribution that we are trying to talk about. You see that for the 1s orbital there is no Laguerre contribution because it's equal to 1. For the 2s orbital you get something like 2 minus sigma, and for the 3s you get something like 27 minus 18 sig rho. I don't know why I kept writing sigma. Sorry about that. So let me continue with sigma so that I keep it consistent. To sigma square. So you are able to realize that the S1s orbital will have a 0 probability only at the nucleus and at infinity, while on the other hand the 2s orbital will also have it at sigma equal to 2, basically at 2a0. And then the 3s orbital, which we will see in a moment, we will also be able to understand what ends up happening here. This will have sigma at 0, sigma at infinity, and also two different values at which the R component, basically the radial nodes, end up coming. Okay, so given a set of wave functions, you should be able to decide what are the n, L, and m values that might end up coming up. So let's take a closer look at their radial dependence, and this is something that we had discussed earlier, but I felt this might be important for people to understand. As we were able to accept, A0 becomes the maxima here, and in this case it will be slightly lower than A0, and this is much farther than A0. This is 6 A0, right? And at the same time, if you go to something like the 3s orbital, it's going to be much farther than whatever you anticipated for the 2s orbital, and it goes with something like the n square dependence. It goes much farther and farther away as you go with the n quantum number value. And the important thing one has to realize is that for the 2s orbital you have one node between 0 and infinity, for the 3s you have two nodes between 0 and infinity, and this is not surprising because you had a sigma power 2 dependence, which is a quadratic equation. When you solve you get two roots, so therefore you end up getting two values that go to 0. And similar to the 1s orbital, the 2p orbital, the first p orbital also has no nodes between 0 and infinity, and the moment you go to the 3p orbital, you have one node between 0 and infinity. Similar is the case with the 3d orbital, where the first 3d orbital has no nodes between 0 and infinity, and if you go to 4d, you're going to have one node. So the radial nodes end up being as n minus L minus 1. This comes up because of the Laguerre dependence that ends up coming. Okay, so once you have a dependence of this sort, you will start appreciating the fact, even if I give you the wave function or the radial dependence, you will be able to predict what are the n, L, and m values that are present. Okay, now having understood this, there are a few other features one must appreciate. That is the fact that, let me erase a little bit. The other fact that one must appreciate is that as you go farther, from the 1s orbital you had only one maxima, for the 2s you have two maxima, and for the 3s you end up having three maxima that ends up coming. Okay, this is once again not surprising looking at the functional form that you are looking at. Remember, we are plotting probability, which is r square dr times the entire function psi nm star times psi nlm. Okay, that's what is ending up being plotted. So you're going to have positive in both of the cases. However, if you're trying to plot psi as a function of r by a naught, this is going to be a slightly different case. This is largely because for the 1s, you're once again going to reproduce whatever you end up getting, something of this sort. Of course, this will not be as narrow as you end up seeing. It will be much more broader because it's not a psi square that ends up coming. And since the values are all less than 1, psi square will be little more broader than rather. Okay, I have to edit this part out. Okay, so now coming back to the plot of the 2s orbital for psi of r over a naught, you are able to realize there is a value, that is when rho is greater than 2, the term 2 minus sigma is going to be less than 0, meaning that it goes negative. So you're going to have something like this that ends up coming, that provides the phase for your orbital functions that you end up seeing. Similar is the case for the 2p orbital. For instance, you are able to see you have no radial nodes for the 2p orbital, however the angular part ends up giving one. So let's take a closer look at it again. So you have a function that goes of the form psi, let's say 2, 1, 0 is going to be of the form sigma times e power minus sigma by 2 times cos theta. Okay, so when you have such a term that ends up coming, one has to realize that there are no radial nodes apart from sigma equal to 0, which we know for a fact, and also sigma tends to infinity. Okay, that also we know for a fact. As the electron goes really farther away, you have very less probability of finding it. However, the cos theta term ends up giving the nodes because the value of theta ranges between 0 to pi, right? And at theta equal to pi by 2, cos theta ends up having a node. Cos pi by 2 is equal to 0 in that case. Okay, now having seen that, let's try to plot the same things. So you had x, y and z, and you had the value theta, the angle theta defined this way. So as theta is 0, you have the maximum value, and you go close to pi by 2, you go through a minimum value. So let's plot 0 to pi for cos theta. So what is going to end up happening? You're going to have this kind of a function where this is going to be at pi by 2, and you have value of plus 1 and minus 1. So you realize that any value that goes beyond pi by 2, you get a negative value for psi. This is once again why whenever you draw p orbitals, let's draw the Pz orbital. Whenever you draw the Pz orbital, you get something of this sort. You draw a plus and a minus here. The minus just indicates the value of the wave function, and you are able to appreciate from the fact that the cos theta ends up making something of that sort. Psi 2, 1 plus minus 1. So that is also going to be of the same radial dependent. We have already discussed this part. And of course, you have a sine theta times e power plus minus I phi. Cos phi plus minus I sine phi. So you have two components that come, the theta that could go to 0 or the phi component that could end up going to 0. And between the same limits of 0 to pi, you realize at 0 and at pi, sine theta goes to 0, and at pi by 2, it's the maximum. On the other hand, phi goes between 0 to 2 pi. When both of these are put together, you get the dependence of psi 2, 1 plus minus 1, where theta ends up going to 0 at sine theta is equal to 0 at theta equal to 0 on pi, and the cos phi part will be 0, will be equal to 0 when phi is equal to pi by 2 or 3 pi by 2, and the sine phi part will be equal to 0 at phi equal to 0 and pi. So once these values end up coming, and if you calmly plot it down, what you will end up seeing is that for these two contributions, I am not plotting px or py. Since there is an imaginary contribution, this becomes difficult. So therefore, what we end up doing is that we might end up doing linear combinations of y2 plus minus 1. Why do we end up doing this? Is because you realize that the mod of y2 1 plus 1, square and y21 minus 1 the whole square, where this is n, l and m values that you're looking at, these are equal to each other. This is largely because whenever you're taking a mod square, you need to do y2 plus 1 star y21 minus 1. And since you have an e power plus I phi term, that will become, since you have an e power plus I phi term here, that will become a e power minus I phi term in this case. So therefore, the y21 plus 1 complex conjugate is actually equal to y21 minus 1. So therefore, these magnitudes become equal. And on top of it, you might remember that the energy for a given value is given only by the n value. So therefore, these two are degenerate in the absence of a magnetic field. So therefore, what we end up doing for the px orbital, we start doing linear combinations with certain normalization constant time. 2, 1, let's say plus 1. Plus 1 plus y21 minus 1. So this kind of a combination comes up, and for the py, it's going to be another linear combination with a minus. Okay, so the only difference that comes up will be this and this, in which case this might end up becoming sine theta times cos phi, and this might end up becoming sine theta times sine phi. Okay, so now you are able to realize that these two can be applied independently of each other, and therefore one can actually plot the px orbital as the x orbital that goes along x and the y orbital that goes along y. Okay, and the plus and the minus indicate the sign of the wave function that ends up coming up in these cases. Okay, now having seen this, why don't we look at yet another aspect of these functions? Psi n, l and m are contributed by the radial part and the angular part. So this is the radial part and this is the angular part. And radial nodes come up as n minus l minus 1, while angular nodes are determined by theta and phi, with the values given as theta less than or equal to pi, 0 less than or equal to phi less than or equal to 2 pi. So these decide the angular node, while n minus l minus 1 ends up, these are the Laguerre polynomials that end up deciding the radial nodes. Having understood this, we see that the wave function, if we have to plot it, is a complex combination of these two, which might not be easy to visualize. Okay, so this is a dot representation. What you end up seeing here is that for the 1s orbital, it is going to only have a positive value. So you have all the colors in orange here. So let's say orange is positive and black in this dot plot is negative. And immediately the moment you go to the 2s, you are able to understand is that you have a node that ends up coming here. Let me try to take a laser pointer. So you're able to realize there is a node that comes up in between the positive and the negative part of the wave function, and this is the node that's given by at sigma is equal to 2, right? So once you get sigma equal to 2, you have a node there, and this is the other sign of the wave function. So basically for the 2s orbital, you have a, let's say the inner core is positive, the outer core will be negative in nature. And when you go to the 3s orbital, let's take a quick look at the wave function. 3s orbital had a sigma square and a sigma and a constant term. So this is quadratic equation. You're going to get two roots that end up coming. So you are able to see that manifesting in this, where the inner core is still positive, the next core is negative, and the third core ends up being positive again. So please be very careful looking at the orbitals, and you are able to understand that the sign of the wave function changes depending upon whichever lobe that you are present in. Of course, this doesn't matter once you take the psi square when you're looking at the probability, but this does have its own implication when you're looking at orbital overlaps that end up coming. When you have a positive and negative, that may end up overlapping. Similar is the case for the 2p orbital. We are taking a look at something like 2p0, which has a positive component at the top and therefore the negative component that ends up coming. So taking a quick look at the 3p orbital, 3p0 orbital, what you end up seeing here is a very similar functional dependence that you saw for the 2s. The 3p will have similar dependence as the 2s orbital for the Laguerre polynomial. So you see a sigma and a 6 minus sigma. Sigma will result in a component that has a node at the nucleus, while as 6 minus sigma will give you at sigma equal to 6 as the value. I'm ready to accept that I'm calling rho as sigma. I'm sorry about it, but I'm continuing to call it as sigma the entire lecture. So you have at sigma equal to 6 and another node, and any values for sigma greater than 6, you'll have a negative value for this wave function, so which you are able to appreciate from the fact that this ends up being for sigma less than 6, and this ends up being for sigma greater than 6, and the signs are different with respect to each other. And this is an example of a 3d0 orbital similar to the Pz orbital, where we are able to see it's a linear combination. We will see that the d orbitals are nothing but the linear combinations of the wave functions that come up right here. We are looking at the 3d0 orbital, which is this orbital. In this case, you are able to see there is a 3 cos square theta minus 1. The radial nodes are not present here. As you see, there are no radial nodes for the 3d0 orbital, because sigma 0 will be the nucleus and sigma at infinity will be much farther away from the nucleus. So only the 3 cos square theta minus 1 term comes up. So you are asking, where does 3 cos square theta minus 1 goes to 0? If you calmly sit down and calculate, you will realize that theta will be at 54.7 degrees, which is exactly where you end up seeing the nodes. So basically, the 3d0 orbital does not have a node, does not have a radial node. On the other hand, the angular node comes up because only of the theta term, because there are no phi terms that are present. You see, there are no phi terms, e power 0 phi term that is present. So the nodes come up entirely due to the theta component. And most importantly, for any value that is greater than 54.7 and less than 180 degrees minus 54.7, this entire 3 cos square theta minus 1 term ends up being negative. So end up seeing a negative lobe that comes up here. Same as the case that comes up here, where you have a 180 degrees plus 54.7, beyond which you get a negative term, and 360 minus 54.7, until then you have a negative term. So basically this is what is represented many times when you guys end up drawing as x, y, and z as the dz square orbital, where you have a plus here and you have a minus that comes up in these slopes. So all the wave functions that we ended up looking give you an idea what ends up happening. I hope this was enough for you to understand and appreciate how orbitals are drawn and why you end up using these orbitals in different theory. Take for an example, in inorganic chemistry, you use these orbitals for the crystal field theory, where you try to say when a ligand approaches these orbitals in different ways, the orbitals are perturbed to different magnitudes. These are the d orbital wave functions, that has the radial part and the angular part. We just saw in detail how the 3 cos square theta minus term results in an orbital that looks like the dz square orbital. On the other hand, what ends up happening when you want a dxz orbital, you will have a combination, of course a normalized combination of y21 plus y2 minus 1. Yeah, where this is the L quantum number, that's the M quantum number. And when you have a dyz, it's going to be 1 by square root of 2 y21 minus y2 minus 1. Then when you want to have a dxy, this is going to be 1 by square root of 2 times I times y22 minus y2 minus 2. And a dx square minus y square orbital is going to be a linear combination of y22 plus y2 minus 2. So this nicely indicates the fact how the second order m plus minus 2 are combined with each other to get dx square y minus y square and dxy, while on the first plus minus 1 first order terms, m equal to plus minus 1 terms, are combined to get the dxy and the xz terms in the d orbital. Okay, good. So now, having understood this, let's also take a quick look of how these orbitals look. For the dxy orbital, you're going to have the probability of finding them more in between the plane of x and y. If you slowly sit and calmly think about these functions, you have a sine theta cos theta term. You can even take the sine theta cos theta term and find where they get to 0, and you will be able to find where the 0 crossing ends up coming. In case of the dxz orbital, you are able to realize that the orbitals are in the plane of xz, so that gives you the name why it is given as xz. And if you sit and calmly solve for when sin theta and cos theta goes to 0, you will be able to find where the 0 crossings end up coming and what are the signs. Similar is the case with the Yz orbital, where dyz lies in the plane of yz plane, that is perpendicular to x, and solving the same kind of solutions will end up coming that you got for xz for yz as well, because they have the same sin theta cos theta dependence. Now of course you have a term that will end up being coming as cos phi in one of this and sin phi in one of this. That might end up determining few other nodes that are present. Basically the sin phi and the cos phi term end up aligning these orbitals along the x or the y axis. Whenever you have a cos phi term, you end up aligning along the x axis, and whenever you have the sin phi term, you end up aligning along the y axis. This is exactly same for the p orbitals as well. So whenever you combine the p orbitals, as we are seeing here, the px will have a cos phi term, while the py will have a sin phi term that is present. So once you are able to pick these characteristics up, then we can go towards the dxy orbital, where this ends up aligning the orbitals in the xy plane with the nodes being computed the similar way. Of course, in this case, you're going to have a sin square theta terms times cos 2 phi term, sin 2 phi term. On the other hand, this is going to be sin square theta times cos phi term. That ends up becoming an orbital that looks like this. In this case, the orbitals are aligned along the x1 y plane, while in all the other cases, except for dz square. In dz square also you have it aligned along the z axis, but in all the other cases, xz, yz and xy, they are in between the axis denoted by the Cartesian symbols given here. Okay, so I hope this gives you an understanding how the orbitals come up organically when you end up solving the Schrodinger's equation. As we go on to the next lecture, we'll be looking at how the Zeeman effect plays a role.